Thank you. I just want to unmute myself. I'm not muted. Excellent. Great. Well, that's a good start anyway. So thank you, George is in the background making all this work. I'm generously assuming there are people watching and listening to this because we can't see you, but it's always that ethereal experience of a virtual session. Well, I'd like to welcome everybody to this session. I know we're getting later towards the end of the conference. The impact of constellations on the radio spectrum. Now, to give you some background, I'm from the Royal Astronomical Society, so this is an issue dear to my heart. I'm going to start just by going through some of the stuff we're doing. I hope everybody can see the slides and then bring in the different speakers. You heard earlier on from Andy Lawrence, who talked at great length about the optical spectrum. And what's less well understood, I think, is that the transformation of low Earth orbit with these impressive facilities of constellations is going to have a big impact on radio astronomy too. And it's something we need to think about. I thought it would be quite nice just to say we've sort of been here before. And even right back in 1961, the Americans had Project West Forward, which launched 480 million dipole antennae to create a kind of artificial ionosphere to help with Cold War systems. They thought the Soviets would cut cables, and astronomers protested back then too. So this isn't entirely new, interestingly. It's something we've seen before. There's nice memoranda from the Soviet Union, but also from the UK, from my own organization from the time. And obviously, we've seen a transformative situation where 2 years ago, before people like me were even readily aware of this stuff, frankly, there were about 2,000 satellites in low Earth orbit, and now there are 4,000 and rising. So it's really changing fast. And we think about the stuff Andy Lawrence talks about, the night sky, but actually it's the impact on these major facilities that Simon's going to talk about that concerns organizations like mine the most. We represent professional astronomers, so it's of great interest to us. I should say also, in passing, we're 200 years old, and that was a big thing for us, but that was curtailed a bit by COVID. This square kilometer array project is an example of the kind of thing where the dishes are so sensitive, the signals they detect are so faint that they're potentially swamped by the kind of signals you get from satellite constellations. And we did what all organizations do in these circumstances. When we hear about it, we expressed our concern, and then we started to convene our own working groups and work with others around the world. These acronyms are just the American Astronomical Society, the International Astronomical Union, ourselves, and the European Astronomical Society. And quite quickly, we saw research papers like this seminal one by Olivia Haino and Andy Williams discussing the problem, and those continue. The literature on this is expanding, but actually some of the quantitative work has been hindered by COVID and things are slowing down. So I just wanted to mention our working groups in case anybody on the call is interested in joining them. This is a picture of one of the few times we were actually able to meet. It's mind-blowing, really, isn't it? But there you go. That was a great success in January 2020, and then ever since then we've been doing it online, but it's still been productive nonetheless. We have one now covering radio astronomy, one optical astronomy, and we include, when we can, representatives from industry, from organizations like the Space Agency and STFC and so on, actually. And I think we'd like to expand that to include the CAA now. They're covering some of the remit, and Ofcom too, actually. I've got a call with someone from Ofcom tomorrow. And I think the main thing we're doing is our public policy efforts. We want to get that expert advice. We want to understand the problem. We want to do good quality lobbying. And I think we've made a start on that. We've had things like questions tabled in the House of Commons. We persuaded the Science and Technology Committee to include this in their inquiry into space strategy. And we're actually, I'm pleased to say, and I'm going to make this announcement, we are a supporter, a strong supporter, and that's another word we use, contributor to a bid by SKO in the UK and NUALAB in the US to host an international centre in understanding this problem. So I'm very pleased to say the RAS is supporting that. We hope to hear the outcome of that in the next few weeks. So I would just end that before I bring in all the speakers by saying, please join us if you have something to contribute to this. We really do welcome that. We're very interested in hearing from people. I regularly email the members of the groups the questions to try and understand this landscape better. And we'd really like to hear from you. We're doing it at a European level as well and feeding into the discussions at the UN. And the next event you might be interested in as well after this conference is the Dark and Quiet Skies 2 meeting, which Andy Lawrence mentioned from last year. That's looking at those SATCOM 2 recommendations. It's free to register, and it's from the 3rd to the 7th of October, and you can attend virtually, which is certainly what I plan to do. So I am going to stop now, and if I can tab through my controls properly, we'll stop sharing my screen. because my priority is to bring in the speakers. So I'm pleased to say that the next speaker we have is Simon Garrington, who is from the Jodrell Bank Centre for Astrophysics and a long-standing radio astronomer, and he will be discussing the issues for radio astronomy. So over to you, Simon, if you're able to, if you can share your screen, let's get you started. Thank you.
I hope I'm sharing my screen already. I can see it. I don't know if anyone else can see it yet. Great. Okay, I'll go ahead. Okay, well, I'm Simon Garrington from Jodrell Bank. Radio astronomers have always had to contend with man-made transmissions. They were there before radio astronomy was. And of course, they're stronger than even the brightest natural sources we observe. We had TV transmissions before radio astronomers had even discovered the sun. So how do we deal with that? Well, one route is through frequency allocations, and they were established first in the 1950s. Jan Oort made the request through the ITU for absolute quiet, but only in a few narrow bands. And as a result of that, now somewhat less than 2% of the whole radio spectrum is allocated to RAS. And RAS, sorry, Robert, is not the Royal Astronomical Society, but Radio Astronomy Services. So radio astronomy is recognized as a service like other services in spectrum regulation. And so there is a well-established regulatory regime for protecting spectrum for radio astronomy as other users of the spectrum are protected. But most high-impact observations and current and future facilities are broadband, even full spectrum, capturing many gigahertz of spectrum. And the expansion in the universe takes spectral lines away from their zero redshift protected bands, and there are molecular spectral bands which don't have any protection. So although we can't expect protection outside those bands, if all we had were the protected bands, radio astronomy would be very difficult. So the other way around that is to avoid terrestrial transmissions by going to remote and protected sites, and that's what the biggest and most powerful facilities now, the SKA, for example, in future, are doing. But satellites are, of course, more difficult to avoid, and new mega constellations of satellites in low Earth orbit are a step change in that challenge. There'll be larger numbers of them, as Robert said. They'll be all across the sky. They have wideband transmissions. By virtue of their numbers, they're likely to be lower cost and possibly have a higher failure rate in terms of the control of their transmissions, for example. And just the sheer proliferation of the number of satellites in number and in spectrum will be a challenge. What do they look like? Well, here's a very nice image of the whole sky made by Bob Watson and the Quixote team from Tenerife at 10 gigahertz in the band where TV satellites, for example, and future LEO mega constellations transmit. And you see the geo arc of strong sources across the sky, a couple of dozen of them. And you can see straight away that they're brighter than the sun, brighter than the galactic plane. Even the side lobes from some of those are brighter than the galactic plane. And none of the sort of faint sources that we regularly study are even visible in this also image, which is just an hour or two of data. So the new constellations will, of course, cover the whole sky, and there'll be thousands of objects, this sort of brightness across the sky. Another way of looking at just how strong those signals will be, here's the allowed strength by the FCC and the expected strength from SpaceX, for example. And these are 10s or 100 times brighter than the sun at 10 gigahertz. The sun would be way off the bottom of this plot. And the sun is a couple of megajanskis. Current instruments are designed to detect microjansky sources, and future instruments, SKA, NG, VLA, will reach nanojansky sensitivity. Now this is in the band where satellites will transmit, so we expect those signals to be strong, but we do expect that the adjacent radio astronomy band, so there is a narrow band protected for radio astronomy just below the main downlink band for Starlink, OneWeb, and so on. We do expect that the protection of that will be respected. And some detailed studies of the compatibility, if you like, between the RES band at 10.6, 10.7 gigahertz and the downlink band have been done. And there's a very thorough and detailed report which you can go and look up. And they show through very careful simulations that narrow adjacent band can be protected, provided the lowest channel for OneWeb and Starlink is avoided, at least over those telescopes. And that's generally accepted that will be the case. And so at least that narrow protected band should be okay. But these studies have also looked at wider issues, such as the fact that the strength of these signals may even saturate the receivers, not damage them, but saturate them to create sort of intermodulation products, a bit like the crosstalk that Andy mentioned in the optical case in his talk earlier. And that would exceed the protection threshold in the protection threshold in the RAS protected band. SKAO, for example, have analysed the impact on SKA in South Africa, and their simulations show that the key SKA surveys in this band could take 20 to 70% longer. I'm interested in the impact on interferometers. Radio astronomy arrays combine signals from multiple telescopes to synthesize a larger aperture, and those signals are correlated with a particular delay and fringe rate compensation. Now, satellite signals are visible to multiple telescopes, and they will partially correlate, and in a slightly different way because the delays are incorrect for the satellites. The satellites are moving in a different way from the cosmic sources and so on. And these LEO transmissions will be powerful, numerous, rapidly moving, so they will be a challenge. You can see those correlated signals at L-band, for example, from GNSS, from GLONASS, Iridium, in correlated signals for Merlin on baselines of 100 kilometers or more. And what you get is a combination of where the satellite is compared to where you're pointing, the delay and the delay rate, and so on. And so we've started to do some observations and simulations of what that will be like for new LEO constellations, new software written which will use the knowledge of the telescope reception pattern. We'll need information on the downlink beams. We can calculate the aggregated impact, for example, that's the plan, but also start to look at these aspects for interferometry, such as the delays and delay rates. And here you see some Iridium data as an example. And we can see how multiple passes of Iridium satellites show up in the data and how they're also modulated by the delay for different pairs of telescopes and the delay rate. We can choose to sort of observe the satellites directly. So if I turn off the delay compensation, point the telescope straight up and look in the GNSS band, for example, you see dozens of satellites moving through delay space. So this is a graph, so time is up and delay between a particular pair of telescopes is across. So you see satellites moving through in delay space, and we can associate those with satellites if once we predict the delays from their orbital elements and so on. And you can actually measure the delays this way and even derive the positions for the satellites in a multilateration technique. So that's interesting. I've been showing some results at L-band mostly because our UK network doesn't yet have receivers at 8 to 16 gigahertz, which is what we're proposing to do now. And this is a key band for studying the formation of planets, stars, galaxies. This wavelength is a few centimeters. That's the size of the pebbles that coalesce to form planetesimals that become planets. And understanding that pebble phase, and for which you need wavelengths of the same sort of scale as those pebbles is a very key question. And if we get these receivers, then what we want to do is confront this challenge of how we observe with these sort of transmissions in the band ahead of future big instruments like SKA, NG, VLA, etc. on 100-kilometer baselines. And we can test mitigation strategies both by the operators and by telescopes, looking at things which apply to single dishes such as scheduling, blanking, and filtering, but also looking at interferometric specific aspects such as fringe rate, filtering, nulling, and so on. So these were just my key points. I think the new constellations present a very real and new threat to radio astronomy by virtue of their number, their distribution, the spectrum they occupy, and potentially quality issues as well. The downlink signals, when you're underneath them in their footprint in band, are of course very bright, but we do expect protection of the adjacent very narrow band, but many observations are broadband, and so will suffer from interference from that downlink band. There will be significant impact, there's no doubt, on SKA, NGVLA, future eMerlin, and VLBI and geodetic observations too. As said, this band, 10 to 12 gigahertz, is absolutely key for planet formation, formation of stars, galaxy evolution, and so on. We expect, as Andy pointed out earlier, there to be a proliferation of operators and further demands on spectrum, not just the band that's currently allocated, but it's easy to imagine there'll be even future demands on spectrum. We're developing software to model that impact, including the aspects specific to interferometry. Some administrations are considering transmission avoidance. So in Germany, an argument is being made via this issue of crosstalk of intermodulation for transmissions to be avoided over the Effelsberg telescope, for example. Some facilities are in discussion with the operators already, and those are nearly all under NDAs. And you can imagine that the topic of geofencing, if you like, avoiding transmission over radio astronomy sites will be key there. There's work at various institutes doing simulations and looking at how to progress this. There's work funded through the EC also called Preserving the Skies. And as we've heard, there's an IAU call for a centre which could be coordinated by ESCO and NOILAB to do all these studies. And just in relation to this conference, there is a connection between some of this work and multilateration observations of satellites, which can be done in both a passive way and using bistatic radar, which we'd be working on with DSDL. So that's it from me. Thank you.
One question in the Q&A. I was going to remember one from earlier because it came up in Andy Lawrence's session, which is about the kind of effects. There's been reference to, I think, 10 to 20% longer needed to collect data. Do you have any feel for what that's going to do to the science if this stuff isn't adequately mitigated?
I think there's, as we see at the moment with all sorts of other interference, it's not just a benign increase in the amount of time required. Some types of observation become almost impossible. Other types of observation may have a more minimal impact. So it's almost a sort of arms race between observational techniques and other transmissions to find a space where you can observe, and that means that some science becomes impossible. So the methanol line at 12.2 gigahertz may well be, which has been vital to studies of star formation and as a probe of galactic dynamics, may become quite difficult to observe, no matter how long you observe for with future constellations.
I can see a question from Courtney, which I think is asking almost about the applicability of your work to other areas. So it says, can the derived location of satellites be used to improve the models used for monitoring space traffic?
So I didn't quite hear the question. I can't see the chat.
Sorry, yeah, apologies. My daughter's piano crack just started up as well, so I can't do much about that. Can the derived location of satellites be used to improve the models used for monitoring space traffic?
I think this way of observing and obtaining positions for satellites is quite interesting. It's certainly a way to go. There are potentially very precise ways of doing this with very long baseline interferometers, and people are looking at precise ways of comparing VLBI-derived positions of GNS satellites in a way to tie together at a very precise level various reference frames, to the extent that it can be used for space traffic. These sort of passive observations, I think, are a useful complement to all the other ways of obtaining positions.
If you've got a very quick answer, if possible, which is Stuart Eves is asking, is there an issue with terrestrial transmissions and space debris reflecting signals back to Earth?
Yeah. Well, I don't know whether there's a problem. I know that the low frequency element of SKA, for which there's a sort of precursor called MWA already in Australia, that can observe, for example, the International Space Station in reflected FM, and there is and that sort of signals a noise of about 10 dB. And the SKA will be about an order of magnitude larger than that. Now, I don't know what the radar cross-section of the International Space Station is compared to space debris, but there's a calculation there to be done. So, but that's one way you could scale it. I mean, say it's 10 dB detection of the ISS at the moment. But obviously that's probably many hundreds of square meters of radar cross-section.
Okay, thank you. All right. Well, I'll leave it there because I know we've got a couple more speakers to bring in. So thank you, and we might get a chance to take some of the other questions towards the end. So I'd like to bring in Liz Quintana now. She's on the in the system, and hopefully there we go. Excellent, great. Welcome, Liz, who's Elizabeth Quintana, and she's got it on her slide. Brilliant. So I can read that out and introduce her, who is the head of satellite industry engagement at Ofcom. We'll be talking about non-GSO orbiting satellites and the spectrum. Over to you, Liz.
Brilliant. Thank you so much. Just to check everyone can hear me, because we've had some technical issues. Wonderful. Good. Thank you to the organisers for what has been a brilliant conference, and for inviting us to be part of this, and to be part of this panel in particular. It falls to me to explain a little bit about what we do in terms of managing spectrum in the UK, and in our role in representing UK interests at international meetings, particularly at the ITU, which is the International Telecommunications Union, one of the oldest bodies, and still one of the most effective bodies for negotiations with all countries in the space community. So Ofcom represents the UK at the ITU, and one of the things that we do, aside from attending meetings in preparation for the kind of the World Radio Communications Conference, which is when we update the rules every 4 years for how countries operate spectrum around the world, is that we manage UK filings. And why are filings important? Well, satellites, as you may have noticed, are global services, and therefore their signals can be received, and they can receive signals from all around the world. And therefore it's really, really important that the frequencies that they use are coordinated globally, so that they don't receive interference and so that they don't cause interference. And obviously this applies for all different types of services that use the radio spectrum, but for services where they are global, so like space, or the maritime industry, or the aviation industry, this is particularly important. So when a satellite company comes and requests for a satellite filing, they are basically requesting to use particular frequencies at specified orbits, or at particular orbital slots in the geostationary arc, and to use those specified frequencies. You can have one satellite, you can have several satellites in that filing, but it's basically a request. And then that goes into a queue of all the other requests, and you have 7 years with which to bring that request into fruition. And as normally, that indicates the level of maturity of your filing. by the time you have brought into use your filing and started deploying your satellites, hopefully the newer filings are a bit behind you in terms of their deployment, and therefore they should protect your existing service. And so having an older filing confers certain advantages, if you like. Although, as we will see, there are some now, because of the as alluded, the cheapness of satellites and of space launch services. There are some that are able to deploy faster than others, and that's causing a few challenges with the current system. Back in the UK, we are responsible for the authorization of all radio equipment and radio systems within the UK. And as you might have experienced personally, there are more and more systems that are looking to transmit wirelessly. And so it is becoming an increasingly interesting task to manage the use of spectrum within the UK. We have recently put out a new spectrum strategy for how we are enabling innovation, because there are many, many new and exciting services looking to use the spectrum. And our kind of main aim is to enable as many of these services to coexist safely and happily alongside each other, and to enable sharing, but also to ensure that spectrum users don't use more than they should, so they stay within their allocated slots, and also that they don't listen beyond the frequencies that have been given to them. So their receivers should also be filtered suitably, so that they are not experiencing interference from services who have every right to operate within the frequencies that they use. Our general objectives are set out in the Communications Act and the Wireless Telegraphy Act. Sorry, this is very boring, but broadly speaking, we are obliged to further the interests of citizens and consumers, and we do that by promoting competition and securing the optimal use of radio spectrum. And as all regulators, we are compelled to act in a proportionate and transparent way in everything that we do. One thing to point out, and I will be coming onto this later, we have been looking to address how we license non-geostationary satellites in the UK. And there has been some confusion in what was said in that particular document, but our national licensing sits separate to our responsibilities internationally, including for satellite filings, but that does not, they are both equally important, and one does not take over the other. Okay, just a quick canter through some of the very wide range of space services that use the radio and microwave frequencies that we regulate. One that people don't tend to appreciate is a bit like radio astronomers. The weather forecasters monitor or use particular frequencies to measure the presence of water, moisture, and rain and ice. So some frequencies are really, really important for accurate weather forecasting, and for that time, the climate change measurements over time. And so access to those bands in a quiet way is really, really important. We do a lot internationally to make sure that those frequencies remain clear and that those measurements remain accurate. We also work very closely with the radio astronomers. Looking forward to our meeting tomorrow, and we protect their ability to measure in the bands they've been allocated in the UK, which helps our understanding of the solar system and the wider universe, as explained very openly just prior to me. We allow or enable tracking and telemetry and control of both satellites and soon space launch from the UK. We also have seen a number of downlinking sites for Earth observation. There is one at Harwell supporting data down from the Sentinel satellites that ESA have. But most of our work is done in satellite communications, as you might imagine that's the transmission to and receiving of signals from satellites in the UK, and that may be broadband services, it may be voice communication services, Internet of Things now, and I believe we even have some near space and deep space communications as well. So all very exciting, and even in that area, which we are very familiar with, there are an increasing number of new and innovative services coming along. You are all very familiar with the GPS system and other global navigation satellite services, and clearly your phone and others rely on the signals transmitted by those satellites from space to geolocate. But also there are satellites, most pertinent for this particular conferences, there are radars in the UK that enable the tracking of space objects in space. And this sits alongside all the many other services that also use the spectrum in the UK. So why are we particularly interested in LEO and MEO constellations? And here I apologise for the difference in acronyms, but we tend to, in the ITU community, refer to these systems as NGSOs, so anything that is not stationary, effectively. And the reason why these are so different is that geostationary, as the name applies, is a fairly static system. The satellite is in a fixed position relative to the ground. The gateway Earth stations point at a particular point in the sky, and as do user terminals. Non-geostationary, clearly, and I am teaching you all to suck eggs here, need to track a number of satellites as they go through the sky and hand off and track the next one in order to maintain that continuous signal. So clearly the transmissions are more dynamic, the satellite objects are more dynamic, and as we'll see in the next slide, that has the potential to have a few possibly temporary problems, but ones that we want to avoid. The key point here is that all satellite broadband services are operating on particular designated channels as laid out by the ITU, but they all are permitted to use the same frequencies. And if you remember, we talked about satellite filings in the first place, then satellite operators go to other satellite operators and negotiate how they are going to avoid each other, avoid interference, and that normally for terrestrial services requires avoiding each other in terms of time, in terms of frequency, or in terms of place. But as we have described before, the presence of many satellites at many orbits and with many constellations makes that negotiation more challenging. For geostationary satellites, they tend only to need to worry about the satellites that are in their immediate vicinity on the geostationary arc, typically within 2 degrees. For non-geostationary constellations, clearly they need to be concerned with nearly all the other constellations that are operating in their frequencies. And in some ways, this is where the filing priority becomes important, but even then, it is proving to be a bit more challenging. So the main challenge that we are worried about, and we at Ofcom are very interested in enabling non-geostationary constellations because of their ability to reach parts of the UK that terrestrial broadband services like fibre, fixed wireless access, and mobile even, it's not cost effective to reach. There's a decreasing number of areas where that is the case, but clearly we and the government are very interested in making sure that everybody has access to decent broadband. And so we're very keen to enable these services. What we're less keen on is a situation where consumers may experience a less than satisfactory service. And because these coordination agreements are harder and constellations are deploying today, that we feel there is a greater risk of what we have termed as inline events. And this is where, if I draw your attention to the image on the top right, two satellites from two different constellations transmitting on the same frequencies are looking to transmit to Earth stations, gateway Earth stations, which connect to the internet, that are relatively close by, and so the signals would cancel each other out and they would experience interference. Gateways in particular are more of a challenge for inline events because they control the access and the information that a number of user terminals will receive, and so those are the most kind of concerning challenge cases of interference. On the bottom left, you have a similar case of interference experienced by user terminals, individual user terminals, where again, from their point of view, in their particular part of the UK, they would see two satellites as an inline event. Okay, yep. So they may be brief, but we want to avoid any particular loss of service. So we, as I mentioned, we have a new consultation out, which is introducing a new process for licensing gateways and user terminals in the UK. We have some new terms that apply to both satellite operators and those applying for gateway licenses. And we're also investing in monitoring these constellations in the UK, and in three ways. One is interference into geostationary services, because those still continue to be important in the UK, particularly for broadcast, but also other broadband services. Interference between NGSO constellations, and also interference from NGSO services to terrestrial services, which might include radio astronomy, as we've seen. So I think that's everything. In summary, we do believe that they have a very important role to play. We are looking to enable a competitive environment, but the dynamic nature of NGSO constellations means there's greater risk of interference. We've put forward some proposals for updating our licensing processes in order to better manage some of this. We do not intend to upend anything that's happening internationally, and we're working very hard at the ITU to help resolve some of these issues. And some longer term trends in NGSO alongside other spectrum issues for space will be discussed in our space sector spectrum strategy to be published in the autumn. Thank you. Apologies for being a bit late.
Thank you, Liz. Much appreciated. Yeah, I'm keeping us to time nicely, but you weren't really overrunning. We were just warning you, as you said earlier, I know. We've got one question here from Catherine Courtney, which is actually something I've thought about as well, which is whether the regulation the current regulation is necessarily, the regulatory framework rather, is necessarily fit for purpose in accommodating new constellations. But the question from Catherine is if she's asking if you can tell us a bit about how spectrum filing decisions will be coordinated with operational licensing decisions taken by the CAA. Now, I freely admit that it seems sometimes a confusing landscape, the way you've got the different bodies that are taking different parts of the decision process for licensing satellites and how they coordinate that with, well, users like Simon, for example.
Yeah, so we do talk regularly with the CAA, and particularly when there are decisions that affect both of us. If we receive an application for a filing, we do ask questions around launch and licenses as they get closer to the end of their filing period, and they're looking to launch. So we do make sure that that is in place, and again we both talk to each other. So if they receive an application for a license, they check with us whether they have received we received a filing too. Filings take a bit longer than satellite licenses, and you don't have to file and license through the same country. So that can sometimes be a bit more complicated, but we do regularly talk to each other. So.
Okay, thank you. I don't know if we've got much time for any more questions, actually. So I might pick it up at the end, but I'd thank you. That's very, very interesting to hear. Okay, all right. Well, thank you so much once again. And I'll be pleased to meet you tomorrow, just so people on the call know we're talking now as well. And our final speaker in this session is Martin Coleman, who is from the Satellite Innovation Group. So hopefully we can move Martin across now. You can see him in the green room in the preview. Excellent. Welcome, Martin.
Thank you, Robert. Okay. Well, thank you. Thank you to Simon and Liz too, because Satcom's Innovation Group, just very quickly, if you like, it's the sort of practical end of the dear old subject of radio frequency interference for commercial systems, commercial space. In its various guises for over 20 years now, has been dealing with that on the international scene, mainly between, obviously, satellite operators, the engineering end of satellite operations, and, of course, the companies that are involved with bits and pieces that go around that subject. So that's where I come from. And I think what I'm hoping to do now is try and take us down a slightly more practical route of what we see the drivers for interference. And I mean, Liz, thank you, covered nearly everything there. Did me a favour there. I didn't have to explain anything else on that one. So thank you, Liz. So without further ado, let's have a look. So what's now? Well, we all know what now is. It's busy. And remember, I'm thinking commercial space. I'm thinking within the confines of near Earth compared to the astronomers. But wherever we look, we have to look after spectrum. If we don't look after spectrum at our level, then everybody else gets affected. That's the end of that story. It's a problem, always has been. I guess from the geo point of view, we're pretty knowledgeable about RFI. We're pretty comfortable with it almost now, and we have the tools and the infrastructure to deal with RFI as we knew it, is what I'm going to say. Because if we think now, what are the challenges? Well, obviously, LEO is a challenge. But on top of that, it's what we use within the systems, both ground and space. And space is probably the easier one to deal with in this respect. But of course, the famous topic of flat panel antennas. Pretty contentious subjects, both of them, but they are the exciting future of space. And to make all this happen, we need fast, flexible, multi-beam performance, both ground and space, to make this work. But of course, you can imagine from SIG's point of view, engineers, we're a tiny bit skeptical, aren't we? We start off a little bit skeptical. It bothers us, but we need to look at it because we think there's a new way of looking at spectrum management entirely. And if we think about it, you think of space situational awareness, and everybody's on the debris case, and rightly so. But we certainly as a group since 2018 have sort of started to think about spectrum as in a situational awareness manner. In other words, we see, and we come up with this term S3A. We've added the third S in the SSA, so it's SSSA, spectrum, in the sense that we see RFI, the new RFI, as a conjunction problem because, as Liz said earlier, everything's on the move down here in NGSO, and elsewhere we've got the MEO orbits to think about. But right now we're concentrating on that effects from our standard geo point of view, and now thinking what happens, how does it work, and what sort of scenarios, problems are we going to run into? So that's what we're sort of looking at. S3A is our sort of term for this now. So thinking RFI conjunctions, we've got new technology in space. I mean, the whole thing with Eutelsat Quantum now is the fact they control by software definition, not just switching and services in the normal sense within the satellite, which is relatively common, but now it's about affecting where you transmit, type of beams, where the beams form, what frequencies are used, etc., etc. So this is becoming, space is actually becoming where the flat panel side, even if they're not so flat, the phased array, flat panel type of effect is actually more applicable now and is in space. And that is where the advantage is right now for the ground to still be using parabolics, because as we all know, the problem with FPAs right now is a cost issue. And although we know they work, we've got the fundamentals there now, I think there's probably enough out there to tell us it works. In terms of working for a cost and doing everything we wanted to do on the ground, there's an issue there. There's a big question mark, and when. So in the meantime, space is probably the place to do this now and is doing this. So for us here, we've been starting to looking at what do we see in RF. And before anybody worries, we're not monitoring content or anything. We're just looking at radio frequencies, transmissions coming down. At the moment, we're looking at Starlink and OneWeb in particular, because in the KU band is where their user frequencies are, and they've got telemetry there as well. So we started just to look, because we need to start thinking about what is actually happening with these systems, what they look like. So we've started doing some bench tests here, right here in the shed in Dorset, but I've got colleagues dotted around the country doing similar now. And we're just starting to get our feet under the table on this and start to get this sort of project going, because we need to look at what we're looking at. We need to understand everything. You saw some of the diagrams that Liz showed that show you the scenarios we think, but we want to start seeing if we can see it. What's it look like? What are we looking for? Again, it's all to do with conjunction. And the best way to look at this is, if we look at this, that's what Starlink looks like from afar. And if we track one satellite, we look at one as we zoom into Dorset here in the UK, we come in and we focus in where my location is, and we're following one particular Starlink 2379 earlier today, which is going to pass very close to us. And what's going to happen is, I'm just checking that at zenith, I can see, what am I going to see? And we found that we can actually monitor the telemetry at the moment, because user traffic here is quite light. But you can see we've actually also got a physical conjunction happening, that we got two Starlinks happening at the same time. And if you look carefully, you can see in a moment, you'll see the telemetry peaking, and you'll see that we start to see, and this is quite messy at this point, because there's actually two sets of telemetry coming in at the same time. Okay, this is very simple stuff. This is right at the beginning, but you can imagine now, we can now point our dishes in the sense of being a user and start to see what we see, and see what conjunction analysis against RF transmissions starts to look like. So the issues, what are we really thinking here? Well, geo, we're sort of looking, for now, we're looking at RFI from the north and south latitudes of 20 to 60 degrees. And we've also got the equatorial region, and we're not sure about those limits, because if you think about the different ways that the Starlink works, for instance, where it transmits south, so that dishes point north, it's always pointing into the back of geo dishes because they're pointing south already. But when you get to the equator, you start to overlap. Transmissions can go over the top. And again, if you think about it, the dishes are reversed and everything starts to possibly cause a problem. Now, we know Starlink and others have got that take in the fact that they switch off, don't use when you get into those particular areas where you're starting to focus on geo. Good news at the moment, folks, is that we've been looking in our area, and the diagram there is just showing you where we look for a conjunction of a Starlink going through the beam to my reference sites, which is dear old Astra, the Astra fleet. And we've got a point in France, where we track and look at Starlink there effectively, and then check from, if you like, my point of view, am I seeing anything from a Starlink system? And we've had others doing this for a while now. And the good news is, certainly in the 20 to 60 area, it's looking good. And even we have had a colleague of ours looking at the equatorial end. It's down in Singapore. And again, nothing's been seen so far. But we're only just got this going literally in the last couple of weeks. So we're just at the beginning of starting to, instead of talking about this as though we do know things, we've decided we don't know things. We want to understand the radio frequency spectrum being used, how it's being used, what the dynamics are, and has everybody thought everything through? I think most of this is coming out as good news. So that's what we're looking at there. And of course, with LEO, as Liz pointed out, we're looking at RFI within a constellation, and of course, RFI between constellations. So these are fairly simple areas at the moment, and we've got a raft of ideas to come from this. But there are 4 areas that we're starting to look at here and starting to see what we can see. So the ground infrastructure is probably behind the times, if anything, in this case. Most of Starlink is controlled from space, scheduled from space at the satellite point. We looked at quantum, we think about different antennas. The clever stuff is actually in space, which is good because it means we can use ordinary parabolics here on the ground, which is cost-wise great. But the FPAs are going to happen. And we've had this recent formation of an independent space industry group to look at the whole interoperability. And of course, whether you call whatever G you like, but let's call it 5G for a minute. They're the big movers out there that need pulling together and making space and terrestrial work seamlessly and work well. So that's it from me. I just try to give a practical look at what we're all trying to look at and get that thought over to you all, that we're looking at this as in more of a conjunction analysis rather than just spot RFI incidents that we are normally used to in the GEO. Thank you.
Thank you, Martin, for that succinct summary. Right, I'm just going to have a look at our Q&A box. Okay, I don't think we've got one directly here, but I was going to ask you, actually, you referred to it as good news.
Well, we had to, come on.
Yeah, absolutely. Fancy perspective. So I was going to, are you, that if you end up with many global players, that this will be such good news? Do you think they'll all be designing systems that are quite as good, and will they play nicely together? Or is that something, that just needs more work to understand?
Well, there's an interesting thought. We ought to have Liz on this one too, because of the thought about licensing, who's responsible for what. I'm going to be my cup's half full. I'm going to be positive in that I think it will, but I think a lot of us have got to do work that helps the Starlinks and the OneWebs of this world and the Telesats make sure they're reviewing what they're doing. And I think monitoring systems, and I think actually the way they schedule and control has got to be up there now. And you've heard from Gwyn Shotwell recently that they're pulling off the recent satellite launches into the next branch and the next era of satellites, because I think they bluntly put it, they've made mistakes and they need to improve. And I think this is something to do with it. But the worry is about that quantity. And you just saw that little excerpt of a film there of a typical what's going on above me in Dorset. You multiply that about 10 times, things are going to get complicated. I tell you now, I see 3 conjunctions of Starlink over Dorset right above me about probably twice an hour. 2s, certainly 6 an hour, and the rest are somewhere between 2 to 10 minutes, regular singles go over. So if that's just Starlink, you add OneWeb into this, you add Starlink into this, you add perhaps Amazon into this, I am concerned. Now, this is the pessimism starting to creep in. This is why we've decided to have a look. We talk a lot, and people have made assumptions, and I'm sure the maths is brilliant. I'm not very good at that. So I need to look at things. I'm a practical guy, and my engineers are helping us do this. We're using very simple equipment here, but it works. And we've had some of this already checked out with more accurate equipment, and we are seeing like-for-like results. So again, beginning of an experiment, but we want the experiment to help. But the look and feel at the moment is not bad. It's not quite as bad as we all thought it was because we've never looked. So I'm going for fingers crossed and that. But I think we've got to work harder. Otherwise, the astronomers of this world and everybody will get affected by this.
And will be noisy. No, thank you.
Yes.
One very quick question from Catherine, if you can answer it in 20 seconds. He's asking where should R&D be focused to tackle these issues? And then I think we have to go and join the sharing session up.
Well, I think R&D should be focused where we're focused right now. We should be looking. We should have more universities involved. I think that would be great. It's not expensive. I'm using a second-hand Sky Dish that was lurking around in the shed, and it works. It's not difficult. Yes, there's some measurement equipment, but overall, I think we need to spread this out. It could even become STEM subject. It could even use everything we've got. If we got data and everybody monitored, we'd find the scenarios. And maybe we'd find the ones that nobody out there has thought of yet. That's what I'm looking for.
Okay. All right. Thank you. That's much appreciated. And I think you probably do have the UK's most sophisticated shed there, Martin. So
it's very kind of you.
Let's see everybody. If I can ask everybody now to, thanks to all our speakers again, and if I can ask everybody now to move across to the next session, which is where we're going to give the feedback from that. So thank you, and I'll see you there. Thanks, George.